Let's talk about differential equations as mathematical models. Let's create a differential equation that is a mathematical model for this situation. The population of a particular country is increasing at a rate proportional to the population. This, in general, is how countries' populations increase, because the more people you have, the more your population is going to increase. A population of 10 million people will increase by more people than a population of 1 million people or 100,000 people. Let's let P equal the population of the country. What we could do is write dp dt equals k times P. In other words, this is the rate, dp dt is the rate at which the population of the country is changing, the rate at which it is growing. And that's going to be proportional to P. So in other words, it's going to be some constant K times P. There's an old-fashioned way we write this. This is another way of saying that dp dt is proportional to P. The textbook author uses this, and I don't think too many other people use this nowadays, to be honest. It's an archaic symbol. Radioactive substances decay at a rate proportional to the mass of the substance present. Okay, we're going to let m equal the mass of the substance present, the mass of this radioactive substance. We'd have dm dt equals km. This is the rate at which the mass is changing, the rate at which the mass of this radioactive substance is changing, and it's going to be proportional to the mass of the substance. The population of a particular country is increasing at a rate jointly proportional to the population and the difference between the ratio of the population to the carrying capacity, n. What? What is that? Okay, so we end up with dp dt equals k times P times 1 minus P over n. Let me walk you through this, otherwise you're not going to get this. But it's cool. It does make sense, and it is realistic. Okay, so this is the rate at which the population is growing, dp dt. We're told that it's jointly proportional to the population, so jointly proportional. It's going to be k times the population, and the difference between 1, so in other words, it's going to be 1 minus something, and the ratio of the population to the carrying capacity, n. So in other words, it's going to be 1 minus P over n. So P is the population, n is the carrying capacity. That's the maximum population possible. The velocity ds dt of a falling object is proportional to the length of the time t the object has been falling. First, why use ds dt for velocity? Where does that s come from? We often use s for the position of the objects. So ds dt is the rate at which s, the position, is changing, namely velocity. That's what velocity is, the rate at which position is changing. Okay, so we end up with ds dt equals k times t. So the velocity is proportional to the length of the time the object has been falling. ds dt equals k times t. Torricelli's law. When water drains from a tank, the rate at which the depth of the water is changing is proportional to the square root of the depth of the water. And this is true. This is not just something we're making up. Let h be the depth of the water. I'm not going to use d for depth because then you have dd dt and it's just kind of awkward. So h is the depth of the water. We would represent in this way. So dh dt is the rate at which the depth of the water is changing, and we're told it's proportional to the square root of the depth of the water. See anything missing here? Yeah, we need to have a k here, so don't just write h or square root h. Got to write k times square root h. Don't forget that. The rate at which the velocity v of a coasting motorboat is changing is proportional to the square of v. This would be dv dt. This is the rate at which the velocity is changing, and we're told it's proportional to the square of v. In other words, dv dt equals k v squared. The acceleration dv dt of a car is proportional to the difference between 180 kilometers an hour and the velocity of the car. So here's how we'd represent that. Acceleration is the rate at which velocity is changing. That's how we define acceleration. So dv dt is proportional to the difference between 180 kilometers an hour and the velocity of the car. In other words, it's k times 180 minus v, where k is some constant. In a city with population p, the rate at which the number of people n who have a disease is changing is proportional to the product of the number of people who have the disease and the number of people who do not have the disease. Oh man, this is a mouthful. So here's the way we'd represent this. The number of people n who have the disease, that's dn dt. and we're told that's proportional to, so in other words, it's going to be k times the number of people who have the disease, that's n, and the number of people who do not have the disease. Well, if p is the total population and n is the number who have the disease, then p minus n is the number of people who don't have the disease. So the way we'd represent this statement as a differential equation is dn dt equals kn times p minus n. And this is a realistic model for the spread of a disease because it's going to be proportional to the number of people who have the disease. The more people you have who have the disease, the more easily it can spread. And it's also going to be proportional to the number of people who don't have the disease, because the more people who don't have the disease, the more people who can catch the disease.